Hi, my name is Sandra Cromer, and this is my third lab report for Physics 2211. This lab can be divided into two parts. In part one, I will find the mass of the black hole using my findings from part one. I will then model the trajectory of a spaceship so that it doesn't crash. To introduce, the purpose of this lab is again to find the mass of the black hole and then create a trajectory allowing a ship to orbit and fly close to the same black hole without crashing into it. Both of these aims will require knowledge and ideas from the concept of gravitational forces. The results show a clear link between the momentum principle and the gravitational force. In this experiment, we must understand two physics principles for both parts. First, Newton's second law, which we can denote mathematically as the net force is equal to the change in momentum over the change in time. Secondly, we must consider the gravitational force, which can be algebraically described as the universal gravitational constant times the mass of the body exerting the force times the mass of the body feeling it, divided by the distance between both point masses squared, and all that times r hat. First of all, we are assuming that the gravitational force from the black hole onto either point mass, whether it's the star or the spaceship, is the only force acting on these bodies. Therefore, the net force is equal to the change in momentum over the change in time, which is then equal to the gravitational force. We also know that the total net force is equal to the parallel net force plus the perpendicular net force, which both can be described as a change in momentum over the change in time, but a different direction. So if the net force is equal to the gravitational force, we can algebraically manipulate this so that the mass is equal to change in momentum over change in time times r squared divided by gravitational constant times the mass of the star. This figure shows the force of the gravity -1 exerts on mass 2. The mass of these bodies are proportional to the magnitude of the force. On the other hand, the distance between both point masses, denoted as r, is inversely proportional, meaning that the smaller the distance between both bodies, the greater the magnitude of the gravitational force. So if we move on to the actual experiment, as I've mentioned, the first part of the modeling involved is calculating the mass of the black hole. This part of the code shows the variables, my email, which generates unique values to calculate the mass, the gravitational constant, the star mass, and delta T, which are all constants instructed. Then we use the first while loop to calculate the velocity of the star in the x and y direction iteratively. The second while loop uses the initial and final velocities from the previous part, which is then used to calculate the initial and final momentum of the star. Then we calculate the change in velocity and momentum to compute the net force, which is then equal to change in momentum over change in time. Using the overall net force, we can then calculate both the net force in the parallel direction and perpendicular direction. Using the net force again, we can calculate the mass of the black hole using the iterative values from the perpendicular and parallel forces. The results show that the mass of the black hole is equal to 1.03782 times 10 to the power of 37 kilograms. This part of the code shows how we will visualize the arrows. As the star gets closer to the black hole, F net and the perpendicular force are at its largest because that's when the force of gravity is felt the strongest, as mentioned in the introduction. For the most part, we can't really see the parallel force, meaning that it has a constant velocity. However, as the star gets closer to the black hole, we can then see a faint hint of the parallel force in a counterclockwise direction. If we move on to the second part of the experiment, we will calculate the trajectory so that the ship doesn't crash into the black hole. The first part of the code shows that the mass of the black hole, a constant we derived from the first part of the experiment, and other constants which were already given in the code. This section of the code shows a while loop used to calculate the trajectory. First, we calculate the net force felt by the planet using the gravitational force equation. The net force on the planet is the sum of the gravitational force the black hole exerts on the planet and plus the gravitational force exerted by the ship on the planet. Then I calculated the net force felt by the spaceship, which is the sum of the gravitational force exerted by the black hole onto the spaceship plus the gravitational force exerted by the planet onto the ship. To calculate both, I had to first calculate the distance between one body to the other, to then calculate the direction so that I could use the actual gravitational force in the introduction. Lastly, I used Newton's second law to update the position and velocity of the planet and the ship iteratively. The results for part two were partly determined by trial and error of the ship's velocity in the x and y direction. To calculate these values, I simply consider not going above the speed of light because that would be physically impossible. So if we move to the reflection, first let's consider, what does this mean? How is the net force and its parallel and perpendicular components different from the rate of change of momentum in its parallel and perpendicular components? If you go back to the introduction, I stated that the change in momentum over change in time is equal to the net force. In part one, we were concluding that the net force was equal to the net force of the parallel component plus the net force of the perpendicular component. So therefore, we're just deducing the fact that they are actually equal to each other. Now let's consider a what if scenario. What if we wanted to orbit around the black hole and then leave? What initial velocity would your spaceship need to have in order to orbit around the black hole? First, the time would need to increase because orbiting around the black hole would take longer, and the velocity would need to be greater, approaching the speed of light. This means that the new trajectory where the ship's velocity in the x direction would actually decrease to negative 2.5 times 10 to the 8th power, and the velocity in the y direction would remain the same. Thank you.